Everybody, Peter Gothen joined us today. Peter did his PhD at University of Warwick, UK, supervised by Nigel Hitchin, with the project entitled Topology of Higgs bundle moduli spaces. Nowadays, Peter works at Universidad de Porto, where he has supervised 6 PhD projects, if I am not mistaken, including mine. Peter is a very productive mathematician with more than 30 research works published. And today, Peter will talk about matrices, geometries, and topology. Welcome, Peter. Thank you for joining us.
Thank you, Ronald. Thank you for the nice introduction, and thank you so much for the invitation. I'm really pleased to be there, well, at least online. So looking forward to maybe someday coming there physically, but for now, I guess this is how things are. So thank you so much for the invitation. I'm very, very pleased. And so maybe without too much ado, I'll start into my talk. So so let me share my so why don't I get my, so for some reason I'm now not getting my iPad up here on the share. Let's see. Okay, so I think I have to maybe share the file on the computer instead. It would seem right. Ah, here. Let's see. Well, this was the only thing I didn't try, of course. Yeah, okay, so if you just bear with me for 1 second, I'll open the file in my computer instead. Because for some reason it didn't come up here. But no problem. Okay, so new page. Okay. So I think this should do. Okay, so I try again. Share screen. Okay. That's it. Okay, so you should see my, do you see my slides now?
Yes, we do.
Yeah, I do. In a reasonable way. Okay.
Yes, it's fine now.
Yeah, it's fine. Okay, fine. Okay, let me go back to my title page. Okay, there we go. So that's it. Okay, so here's my title: Matrices, Geometry, and Topology. So I certainly see here some colleagues for whom some of what I'll say will be a little bit trivial. So I apologize in advance, but so I understand that the main target audience is also the undergraduate population. So I've attempted to make the talk fairly accessible to anybody with a first course on linear algebra. So this was what I was aiming to do. So I'm going to talk about several kinds of geometry. So I'm going to just start very quickly out with Euclidean geometry and a famous story about the fifth postulate of Euclid, and then talk a bit about spherical geometry, and then sort of the opposite direction in which you can go, which is hyperbolic geometry. If you do have questions along the way, so please feel free to ask them or use the chat. Maybe I have it open here. I'll try to answer any questions that you come up with. Please do ask. Anyway, why do we need more than the usual Euclidean geometry we all learn at school? Well, you can come up with several explanations for this, and later on I'm going to give another one. But the first one is the following. Actually, we know that we don't that Euclidean geometry is not the only geometry we need to live in this world, because the Earth that we live on is a surface, and that surface actually doesn't have Euclidean geometry. So here, let me try to get my spotlight up here. So if you look very well, you will see me around this spot here. You probably have to look quite carefully, but I'm there. If I understand correctly, you are all more or less around here. And as you see, the sun is shining where you are, or maybe the sky is gray, but certainly it's daylight, whereas up here it's already dark. So why is that? That's because the Earth is a sphere. And so we need spherical geometry even to describe the world we live in. Okay, so let me get to the second theme of the talk, or the second word in the title, which has to do with matrices. So I want to explain to you how to represent the transformations of a geometry using matrices. So this is just a reminder here that usually plain Euclidean geometry is described using Cartesian coordinates. The point has two real numbers that defines the point. And so we have the Euclidean plane, which is just identified with r squared, so two coordinates for each point. And according to Felix Klein, so more than 100 years ago, he proposed that in fact, not just Euclidean geometry, but any geometry should be studied through the set of transformations that preserves the properties of the geometry. So for example, in Euclidean geometry, we look at the transformations of R2, which preserve the most important notion of Euclidean geometry, which is the distance between 2 points, which is just given, 2 points, which is just given by the Pythagorean theorem. So then when we study linear algebra, we learn that, in fact, isometries of the plane, they can be described in this way. So each point is transformed by a linear map, which is given by multiplication by this 2x2 matrix, and then a translation, which is given by a vector. And if this matrix is orthogonal, then this map is an isometry. And that's if and only if. So an orthogonal matrix means that these two columns of the matrix, that these two vectors are orthogonal unitary vectors. Okay, so that's how you study Euclidean geometry using Cartesian coordinates, and we can represent the isometries through linear transformations, or more generally affine transformations, but where the linear part is given by an orthogonal matrix. So this, of course, is very familiar, and let's then move on then to the world we live in, which is the sphere, and try to see how that kind of geometry, so spherical geometry, actually is different from Euclidean geometry. So let's look at a sphere then and put it into Euclidean 3 space, and so the sphere has a radius r. And let's try to just look at one aspect of the spherical geometry, which is if you look at a triangle. So in all geometries, of course, we always love looking at triangles, and spherical geometry should not be no exception. So let's look at this spherical triangle here. So I have 3 points, and then I have these the vertices of the triangle. Then the triangle should have some sides. And okay, what is the side? So in Euclidean geometry, a side is just a piece of straight line, a segment of straight line. In spherical geometry, you should have the corresponding notion to a straight line, which is a great circle. Why? Because it's, at least in a local sense, it's the shortest path between 2 points. So anybody who navigates the surface of the Earth will want to go along this great circle because it's the shortest path. So we have these 3 great circles, and they intersect in the 3 points A, B, and C, and then we can measure the angles here, and we have the usual notion of triangle with side lengths and angles. Now, if we look at this point A, we know that there'll be an antipodal point over on the other side of the sphere, and then this angle A will sort of open up like a slice of the orange, and the bigger the angle A, the bigger the area of this whole region here, which I denoted by sigma A, and the area will be proportional to, in fact, the angle A. And if the angle A goes up to 2 pi, then the area will be the whole area of the sphere, which we know that's 4 pi times the radius squared. So like that, we can easily determine the area of this slice of, or surface of this slice of orange. And then it's a simple argument to combine that, that idea for the 3 points A, B, and C, and divide the sphere into all these pieces and calculate the area of the triangle. And you reach this formula which says that, in fact, the area of the triangle is r squared times this number, which is the sum of the angles. So they come because of this proportionality, minus pi. So that's maybe at first sight quite a surprise, because you're used to in Euclidean geometry, the sum of the angles is just equal to pi. But here this is not the case. And this is why, because the sphere is a curved surface, and then exactly this constant 1 over r squared is conveniently interpreted as being the curvature of the spherical surface. So another way of understanding that the sphere is a curved surface is if we look at a circle. So what is a circle? It's a set of points at a fixed distance from its center. And in a spherical circle, what happens, since the sphere sort of curves down, the circumference is actually not 2 pi times the radius, but it's a little bit less, because the sphere the circle gets pulled down in the sphere, right? So the radius of the Euclidean circle that corresponds is smaller than taking the radius along a great circle. So this is another manifestation of the fact that we have this positive curvature. And now for one final point, which is important for what I'm going to say, it has to do with parallel lines. So in the Euclidean plane, we define parallel lines as lines that don't intersect. And on the sphere, we can use the same definition. It's just that we don't have any pairs of lines that satisfy this, because any two great circles will intersect in 2 points, in fact. And so in spherical geometry, in fact, there are no parallel lines. Okay, so these are just facts that we notice about the sphere for now, and let's move on and go back to Euclid. So I want to tell you in particular about this famous fifth postulates, but let me just remind you that Euclid based his geometry on 5 postulates that he considered were really self-evident facts about the world around us that you can infer from experience. Okay, he said that this is not things you need to prove. You take this as postulates because they're clear. And he says that we can draw a straight line between any two points. So that by that he means a segment, and you can extend that to an infinite straight line. You can draw a circle, so that means you have a compass, right? So we have no ruler and compass. A nice notion that all right angles are equal to each other, which just sort of translates into the idea that we can move things. So maybe somewhere underlying that, the idea of an isometry. And then there's this fifth postulate, which is the one I want to focus on. So this fifth postulate, you already see it's a long statement, which is much more complicated than the other 4. And it says that if you have the straight line falling on 2 straight lines, makes the interior blah, 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 blah. It's a long and complicated thing, but basically it says that if you have one line, a perpendicular, and another line cutting that perpendicular, or that other line cutting that line, you can look at the 2 angles, the sum of the 2 angles. If that sum is less than 180 degrees, the 2 lines will intersect. So basically it means that to each point outside a line, this is the modern form for that, there's a unique parallel line through that point. So of course, geometers and mathematicians in general love Euclid and have loved him for many years. And many mathematicians felt that this fifth postulate was really a little bit not quite as natural and obvious as the other 4. And there was for a long time the idea that it ought to be possible to prove this fifth postulate instead of taking it as a postulate. So use the other 4 postulates, make logical deductions as in the elements, prove theorems of geometry, and one of the theorems would exactly be this statement of the fifth postulate. But then at some point, after many attempts and after many people actually tried to prove this fifth postulate by contradiction, so let's start by the negation of the fifth postulate, and let's try and see what happens if we develop our geometry based on the 4 usual postulates, 1, 2, 3, 4, and the negation of the fifth. Because if you can prove it, then you must reach a contradiction sooner or later. And some people tried and thought they reached a contradiction, but they didn't. And in the 19th century, yeah, let me just here, sorry, I maybe got a bit ahead of myself because, so this is, let me see here, sorry, yeah. Yeah, exactly. So we try to look then if we cannot reach a contradiction, then it's because, well, there may be actually some geometry where the negation of Euclid's fifth postulate holds. And so what should be the properties of this geometry? So the negation is what I wrote here. This is the negation of the fifth postulate. So if we have a line, a point not on the line, there should be, in fact, more than one, at least two parallel through the given line through that point. And it'll be in a circle in this geometry. In fact, what will happen is that the circumference over the radius will be more than 2 pi. So it's actually the opposite situation of the sphere. And again, a manifestation of the same idea. In a triangle, the sum of the angles will be less than 180. And more precisely, it will be given by the formally similar formula to the spherical geometry, but with a minus here. So in what follows, I'm actually just going to look at r equal to 1 because we don't need to look at all these different sets, but that's a small detail. Okay, so you may try to build this model of a geometry in which the negation of the fifth postulate holds and see if you reach something. So here you see, in fact, something you can do at home, which is to use crochet. So if you know how to do it, at least. If you want a geometry in which the circumference of a circle is actually not proportional to the radius, but grows faster, then you can do that by putting extra threads, extra bits of extra loops into each round. Okay, so normally you would augment proportionally, but you can augment more, and people do this in the right proportion, and you get a surface in space which looks like this. And this would be a surface in which you have a geometry in which the negation of the fifth postulate holds. Here's another way of doing this. Okay, so this is the attempt, and here's the big question, and this is in bold, so this means I should launch my poll, my first poll. So here's my poll. So I just asked you to vote. Do you think that such a geometry exists? So just please vote. Don't think too much about it. Yeah, I guess maybe I've given away the answer. So. But anyway, just to see if you're there.
Solo para saber si están ahí.
Yeah. So
voten, chicos.
Yeah. So. Okay, so yeah, so okay, so a couple of no's and but more yeses, and so these are the results. Okay, so let me close this again, and yes, okay, so now I get a funny noise. Yeah. Well, nobody ever saw an infinite potato chip because this crochet here or this soccer ball actually looks a bit like a Pringle chip, right? And the thing is, can we really expand that infinitely and get a nice surface with the negative curvature geometry? Well, no, that we can't. If we want to have such a geometry with these properties inside the Euclidean 3 space, then we are out of luck. This is not possible, at least if we want the surface to be nice and smooth. The problem is exactly that as you go on with your crochet, the edges of that surface will get so curled up that they'll stop being differentiable. So this is the real problem. However, so now let me come back to the thread where I was getting ahead of myself a little while back. If you do try to prove the fifth postulate from the other ones by proceeding trying to reach a contradiction, after a while, you may, in fact, if you're not prejudiced, realize that nothing is going to go wrong. You just keep proving nice theorems, but you never reach contradictions. And you have very nice results, which in the end, it turns out, in particular these three people whose names are written here, Lobachevsky, Bolyai, and Gauss, independently, all reached the conclusion that in fact we can go on trying to disprove the fifth postulate, but in the end we're just constructing a new geometry in which the negation of the fifth postulate holds. And I think it's necessary to appreciate that at the time was a completely mind-boggling idea, to the point that, for instance, Gauss, who was the greatest mathematician of the time and most famous, simply did not want to publish this. He was too scared of the reaction of the world around him. So it was quite a revolutionary idea. In particular, I think because at the time there was not such a great distinction by physics and geometry. It was really considered, I think, that Euclidean geometry was kind of physics. It was really describing the world around us. So that was like the first phase. And then the question was finally decided because it turned out that it's possible to build a model of this non-Euclidean negative curvature geometry with the properties I was telling you about a little while back. Inside Euclidean geometry, but there's a price to pay. What is the price? The price is that we must change the way we measure distance. So then we can build this new geometry inside Euclidean geometry, and that is a very powerful idea, because if it turned out that this non-Euclidean geometry was inconsistent, if you could reach a contradiction, then if this model is built inside Euclidean geometry, then in fact Euclidean geometry itself is inconsistent. So this discovery of the model is philosophically very, very important, because it shows that the non-Euclidean geometry is as consistent as Euclidean geometry. So really not much hope of inside Euclidean geometry proving the fifth postulate from the other four. Well, with that usually, of course. Yeah. Okay, so let me tell you about two models for this. There are many models. I'm going to tell you about two because I want to get back to my theme, which was the theme of the first theme, which was that of representing isometries with matrices. So I want to show these two models to you. So the first one, in a way, is the nicer of the two because it's more symmetric, and it's just the interior of the unit disk. So let's look at the plane. Think of it as a usual Euclidean plane, but we may conveniently use coordinates in the complex numbers, because then we just need one complex numbers to describe the pair of points, x plus iy. And we look at the interior of the unit disk. And we simply think of the points in the interior of the unit disk as the points of our geometry. And we call this disk D2. It's known as the Poincare disk. And then what is a line? Well, a line is what I'm drawn here. Here are two examples of lines. It's either an open diameter or the open arc of a circle which is orthogonal to the boundary circle here, the blue circle. So that's the model. You may say, well, but it's a geometry, so you need to measure distance. And of course, there is a definition of a distance function, which I'm not going to bother with telling you, but there is a distance function which makes this into a nice, complete geometry, meaning that these lines, in fact, are all isometric to a copy of the real numbers, okay? So what does this mean? This means that the distances become very large as we approach the boundary, okay? So let me give you an idea about how distances are measured here. So this is this famous print of Escher, where he has drawn all these fish, and they are in fact all of the same size in the Poincare disk model. So that means that you can see that the distances become much, much greater as you approach the boundary, right? So there will be an infinite number of fish in the line here as we approach the boundary. So of course the distance function is very different from the Euclidean one. Now let's look at this model, and let's at least see that it has some of the properties that we were looking for. So I did put on the previous slide one important thing, which is that angles, as opposed to distances, are just the usual Euclidean concept. So for example, if I think of this hyperbolic line, which is just a diameter, and I want to know what angle does it make with this line, I just look at the angle here in the center, and I measure it in the usual way. Here's another one. Here's another hyperbolic line. That's this circular arc, which is orthogonal to the boundary circle. And that will intersect maybe this hyperbolic line, which is a diameter. And we can also see that these two hyperbolic lines intersect orthogonally because this angle here is 90 degrees. And now we can see something really really rather nice and interesting, because if we start looking at a point here in the let's look at this line that goes across here. Maybe I have a bit no, I don't, yeah. Maybe let's look here again at this way of drawing things, which has less detail. So here's a line, here's a point, and here's a line, hyperbolic line through that point, which is outside of, let me see if I can draw the point here. No, I can't. Okay, never mind. Okay, but we could easily draw another circular arc, orthogonal to the boundary circle through this point, which does not intersect this diameter. So in fact, the negation of the fifth postulate holds in this model. And of course, you then check that the other postulates all hold. So we have then finally reached the conclusion that yes, what's called hyperbolic geometry, a geometry in which the first four postulates of Euclid holds, but not the fifth. And this is this here is the picture of it that tells you a bit about the distance apart from the line. Okay, so this is a very nice model, but I want to tell you about a second model which is closely related, which is called the upper half plane model. And the reason I tell you about this is because I want to get to the matrices. So we look at complex numbers again as convenient coordinates in the plane, and we look at only the upper half plane, so with complex numbers with imaginary part positive. And this is what I'm saying here. So here's a formula which tells you how to transform the disk into the upper half plane. So you take a complex number W in the open unit disk, and you apply this function to it, and you reach a complex number Z, which is then numbered in the upper half plane, and you can check that this is a bijection, and then you can in fact check a lot more. Instead of thinking more about the formula, let's just look here at a picture that explains what's actually going on. So here in this sphere, I drew the unit disk, so the Poincaré disk, as the disk that bounds the equator. Okay. And here, this green circular arc orthogonal to the boundary is then some hyperbolic line. Okay. Now, the first thing I do, I go to the South Pole and I make a linear projection. So to each point on this in the disk, I draw the line through the point in the South Pole, and then I reach a point on the surface of on the northern hemisphere of the sphere. And like that, my circular arc here gets transformed then into actually to a semicircle. So this vertical cut of the upper hemisphere. Okay, so this transforms my Poincaré disk model of hyperbolic geometry into another model in which the points on the upper hemisphere and the lines are always these semicircles, which are obtained by intersecting the sphere with a vertical plane in space. Now let's take step 2, and let's just fix another point here in the equator, and let's project then these red semicircles. Let's project them onto the tangent plane to the sphere at this opposite point. And then, in fact, that will transform our disk, which was here, centrally horizontally in the sphere, onto this plane, which we have up here. And you can imagine that, okay, certainly we only go to the upper half plane. And if we have a point that's really, really close to our point here in the equator, for example, just here, if we draw the line through these 2 points, we are of course going to go very high up, and so we'll go to infinity in this upper half plane, so at least it looks reasonably enough. And okay, if you work a bit, you can go back and realize that this formula does exactly that. So then we get the upper half plane. What will happen is that the lines then will become semicircles, which are orthogonal to the real line, so or possibly just vertical half lines. Okay, so these are semicircles again, orthogonal to the real line. So the real line is here, and the imaginary numbers are up, right? And this boundary real line of the upper half plane will correspond here to this boundary circle in the disk model. And so here you can see how the distance then gets compared from the disk model, which we have back here. So if we transform this in this way onto the upper half plane, we'll see this pattern of the fish. So you see again, here we are very close to infinity, right? There are infinitely many fish as we approach this real line, which is the boundary, and then here the fish then gets distorted. So certainly again, this is not a Euclidean way of measuring things. It's not a Euclidean distance function, but it's a distance function which is quite different, because again the size in the hyperbolic metric, in the metric that we're using in this geometry in the upper half plane, in this notion of distance, these fish all have the same size. So here are some more clean drawings of what I was just explaining. So these here are all lines in the geometry. So these arcs really represent the shortest path between 2 points in the distance measure we have. They should be orthogonal, these open semicircular arcs. They should be orthogonal to the boundary. And they all are isometric to a copy of the real line with the usual distance on the real line. Here's a formula for the distance. We don't need it for anything. This is just so that you will believe me that there is a good way of measuring the distance between points that makes this into a nice complete geometry in which we again see that the negation of Euclid's parallel postulate holds, right? Here I have a line. Here I have two other lines that intersect in a point that's outside this line. So this vertical line, hyperbolic line, has two distinct parallels through this point here outside. Okay, there's going to be another little formula here, which is that if we're on the imaginary line, there's a slightly easier way of measuring the distance between 2 points, simpler formula. That's not so important. Okay, what I wanted to get to, and what I already mentioned, was that what are the transformations? So let's take Felix Klein seriously and say, okay, we should understand the transformations of our geometry, which are the distance-preserving transformations. So just like those orthogonal matrices and translations in Euclidean geometry, let's try to represent by matrices these isometries. And in this model, this upper half plane model, there's a particularly nice way of doing it, because we can use real 2x2 matrices, just as in Euclidean geometry. But of course, there's a twist. And what is the twist? We don't need to ask the matrix to be orthogonal. We just ask it to have determinant 1, and even that is not that important. What we do with the matrix is that we take this so-called Mobius transformation of the complex numbers. So any complex number z gets transformed into this other complex number az plus b divided by cz plus d. And when the matrix is real, you can check that that this new complex number, if z has positive imaginary path, then so does this new number. So in fact, we transform the upper half plane to itself with this transformation, and in fact, the famous theorem of Poincaré is that this way exactly we can represent all orientation preserving isometries of this upper half plane model of the hyperbolic plane by matrices. I should mention here that this correspondence is not just nice in the way that we can associate these four numbers. We can associate a nice isometry, but even more, in fact, the composition of isometries will correspond to just taking products of the matrices. So the linear algebra of this matrix corresponds nicely to the distance preserving and orientation preserving maps of H2 to itself. If we want isometries that invert the orientation, that's easy enough. We just compose with a reflection. So here with z goes to minus z bar, this reflection the imaginary actions, and it turns out that that's actually also a hyperbolic reflection. So you can compose with that and get all isometries of the hyperbolic plane represented nicely through this linear algebra trick. Okay, so let's see some examples. So I have here, in fact, a list of various kinds of isometries of the hyperbolic plane. So you may remember from your geometry school course that in Euclidean geometry, we have certain types of isometries. We have, for instance, reflections, we have rotations, we have translations, and then actually we have only one more kind, which glide reflections. The list in hyperbolic geometry is a little bit longer. There's all the corresponding kinds of transformations with similar, with not quite the same properties, and then there's a new one called a limit rotation. Okay, it's not super central to us, this classification, and there are these formulas which you can have fun looking at, but I just want to share with you here one example, which is exactly a translation. So here's a little animation. So I hope you can see it. So this is a translation of the upper half plane model. So here we go. So this, let's see. So this could maybe be made a bit bigger so you can see it better. Let me try again. So I hope you get the idea. So this figure here has all the time the same hyperbolic size, okay? And it corresponds to sort of doing a Euclidean translation just of the whole plane continuous along a line with some parameters. Let me just play it to you again. So you see in particular that there is in fact this invariant line of the translation, which is this, let me get the spotlight out here. If you follow along here, you can see that there's a line here that sort of stays the same, which is this semicircle that connects the two red dots. Yeah. And that is actually an invariant line of this translation. So this is how we should imagine some isometry of this particular case of isometry of the hyperbolic plane. I'm just going to show you another one also, which is the same kind of isometry, again, hyperbolic translation, but now in the disk model. So different model, but showing exactly the same kind of isometry. So here you see again, you can see all the points stay at the same distance as this moves along. So in particular, you also see, of course, near the boundary things move much more slowly, reflecting the fact that the distance is much greater than it appears here with our Euclidean eyes. Okay, so let's go back to our main slides. So you can have fun. I put here the link where this Ham Goldman Strauss made these. There's some more nice animations that you can have fun looking at. Okay, so I hope we have an idea about what hyperbolic isometries could look like, how we can represent them by matrices, and so at least have some sort of idea about how we might change our Euclidean glasses into hyperbolic ones. Okay, so now let us move on to the second big theme of what I want to tell you about, which has to do with how might we, instead of trying to have these geometries in the plane, having it on different kinds of surfaces. So we did realize that certain geometries, at least, don't live on the plane. In particular, so I lost my spotlight. Here. No. Do you see my cursor if I use it for pointing?
Yes, I do. I don't know.
You see the cursor?
Yes, I do. Me do.
Okay. So there's a spotlight on Zoom, but it seems to have stopped working. There it went.
There it is.
Yeah. Okay. So we saw that the spherical geometry, which is the geometry of a world, lives on a sphere. However, Euclidean geometry lives, well, on the plane, and the hyperbolic geometry, well, it lives on the upper half plane, but at least topologically, there's no difference to actually the plane, right? It's something that basically can be deformed continuously into the plane. But there are other closed surfaces. So the sphere has this property that it's a closed surface without boundaries. So it's not, hasn't this infinite aspect where you can go off to infinity. When you go around the sphere, you end up in the end coming back to the point, as anybody who tried to sail away into infinity has realized that they'll actually come back. And here's some examples of some closed orientable surfaces. Technical term is that they are compact and without boundary, orientable. So the first example is this donut-shaped surface. So the surface of a donut, we could duplicate that if we need to go to the beach with several people and you don't want to get too far from each other when you go swimming with this boy. You can of course go on. So that's what the dots represent. And so we know that spherical geometry lives in this sphere. But now we have three two-dimensional geometries of one which is spherical, positive curvature, Euclidean, which is zero curvature, and hyperbolic geometry, which is negative curvature. And we might ask, okay, could it be possible, for instance, to have Euclidean geometry on the sphere? Now that we have realized that we don't have to be stuck with the Euclidean distance function, or the one of the space, and inherit it onto the surface, because we realized that, for instance, the crochet didn't work right, so we had to change the distance function to not be the Euclidean one to fit the hyperbolic plane on the disk. So maybe we could, why not fit some Euclidean kind of geometry in the sphere? So here's one particular question of this kind. And this is supposed to be a poll 2, so I would like you to answer this poll. No, this is, yeah, no, this is not what I want. I want to I want to launch the poll, yeah. So can we define a Euclidean distance function on the sphere? Just guess. You don't think too much about it. Just give me your. Okay, so it's not just 5 more seconds and I'll finish. Okay, and you should be able to see the results. Okay, so yeah, 2/3 majority for no. Okay, let's see what happens. We'll try to think about it. And okay, so I'm going to answer a different question, which is how we can define a Euclidean distance function on the torus. But that different question is actually going to help us ask and answer the other one. So this is where I'm going to show you another little video, which is how on the torus we can in fact put the Euclidean geometry. So if you were young, more or less, when I was young, you would play Pacman. If you are young these days and go to university, you may still know what it is, or maybe you don't. But this is a nice computer game where you are this little yellow cheese, and you can go around this maze, and you want to avoid being eaten by all the ghosts. And there's a nice thing about Pacman, which is that you can when you are your little yellow cheese, you can actually go out one side of this maze, and then you just enter on the other side. So that's great for escaping the ghosts. And the game was actually not like that, but you could imagine that you could go out at the top and come back at the bottom. And let's all agree that the geometry of this sphere is Euclidean. So if we just roll that square around a donut-shaped surface, we can do that, roll over and join the ends, and you will get what you see here. And there's of course no reason why you shouldn't take your Euclidean distance function with you from the square to the surface of the torus, and you have a perfectly nice Euclidean geometry here on the surface of the torus, and you can see how the two correspond. So this is indeed possible to have a Euclidean geometry on the the torus. So I hope I'm back here. So this is my limited artistic capabilities. I tried to do the same as you just saw on YouTube. So here we cut open the torus along this circle, this green circle. Let me get my spotlight back. So you cut it open along this green circle and you get a tube. Then you cut it open along this red line and you unfold the tube and you basically get a square. And these arrows indicate how you should glue it back together if you want to go back to the torus. And we declare the distance function to be the one that comes from this Euclidean square, and we are happy we have geometry on a torus. Euclidean geometry on a torus. This slide explains exactly the same thing in more formal mathematical language, so let's not waste too much time on it. I mean, just go to the next one, which is the picture, which is perhaps the most important. So we don't have to make it into a square. This is perhaps the main message here. We could make some parallelogram in the plane, and we could cut the sides of this parallelogram and then identify these opposing sides because they have the same length. And therefore I'll get, if I glue this side of the parallelogram to this side, I'll get a cylindrical Euclidean surface, and then I can close it up, gluing the upper side to the lower side, and I'll get a torus, a donut surface, which has the Euclidean metric exactly in the same way. We can formally write this as the torus being the plane, and you can say it's modulo gamma, where gamma with fine words is this group which is generated by some isometries. So basically what happens is that when I make the gluing in mathematical language, I'm taking a point here on this side and translating it with this vector v over to the other side and identifying the 2 points. So this is what's going on, and I can think of this this surface as in fact associated to this set of isometries which realizes all these identifications of the sides. So it's all these whole plane, and I keep making these identifications and identifying all these parallelograms according to the recipe given by this set of transformations, which can be 1 translation, 2 translations, translations by 3 times the vector, and so on and so forth. Okay. So now let's just go into topology quickly. So the topology will help us answer the question we were looking at before about the possibility of having Euclidean geometry on a sphere. So let me just remind you or tell you that if we have a surface, we can try to understand the topology by cutting it up into triangles. Just doesn't really matter exactly if they are very nice triangles, just some kind of triangles with sides and vertices. And then we can count number of vertices, number of edges, and number of faces. And we can define this number, the Euler characteristic, which is number of vertices minus number of edges plus number of faces. For instance, this picture here, you see a triangulation of a sphere. Well, it's kind of cheating, but anyway. It's basically like the surface of a tetrahedron, right? There are some small technical problems with drawing it like this, but it works perfectly well. And we can check that the Euler characteristic of the sphere is in fact 2. Now, what does this have to do with what we were doing before? Well, it has to do with the following, that if our surface is in fact Euclidean, then if we think of the triangles, we can look at the interior angles at each vertex, and we'll just have a vertex and we'll have some lines going out from it. So if we add up these interior angles, we'll get 2 pi. On the other hand, if we have a triangle and it's a Euclidean triangle, well, we know that the sum of the internal angles is certainly 180 degrees, so that's pi. So if we make the accounting of all these things, we can either count all this sum of angles as the number of triangles times the internal angles in a triangle, which is pi, so this is f times pi. Or for each vertex, we have 2 pi's worth of internal angles, so these 2 numbers have to be the same. Also, if we count the edges and the faces, we'll see that each triangle has 3 edges, and each edge bounds 2 triangles. So in fact, twice the number of edges is going to be 3 times the number of faces, right? You can easily see that here, for instance. So here we have 4 faces and 6 edges, and the combinatorics always have to work out like that. So if you put all this information together, we get that's certainly 0. This 2f is 3f minus 2e, right? This is the second formula. Now I write that as 2f minus 2e plus f, and I use the second formula here, which says that f is 2v, and I put that in, and I have here twice the Euler characteristic, and I know it's 0. So, conclusion: a Euclidean surface must have 0 Euler characteristic. So, sphere, tough luck. 2 is not 0. No Euclidean geometry on the sphere. Okay. What about hyperbolic surfaces? So this was a great success, right? Because the topology of the surface told us something about the geometry that we may have on it. And if you think about what happens in the case of the sphere, really what happened was that because the angle sum in a triangle is actually more than internal angles add to more than pi. When you were making this calculation that 2 pi times the number of vertices is pi times the number of faces, you'll see that you should have had here more than pi times the number of faces, right? This was summing all the internal angles in each triangle. So with that inequality, you get positive Euler characteristic, exactly as we got on the sphere. Now, if we have a hyperbolic surface, we should have exactly the opposite, because the sum of the internal angles in a triangle is less than 180, less than pi. So we should have negative Euler characteristic. And okay, how do you get negative Euler characteristic? Well, you can do it by taking this so-called bi-torus. So what do? Let's just look at the upper. So I take here an octagon, but let's just look at half an octagon. Okay. This half octagon now has these sides, A1, B1, and here opposite A1, opposite B1. So this means that this is a recipe again for stitching together or gluing. So I should identify this A1 side with this A1 side in the direction of the arrow. And I should glue this B1 side with this B1 side in the direction of the arrow. And if you remember how we glued the square to get the torus, we get exactly the same thing. We get kind of a torus, except that now there's this cut here. So really we get a torus with a boundary circle. So this is what you see. Same thing in the lower half. Now we glue the two together along this line here, and we get a bi-torus. And it's an exercise for you now to really fast make a triangulation of this. And here's then my third pole, I think, which is to guess what will be the Euler characteristic of this bi-torus. So I'll see a few answers. Don't be shy, just guess.
No sean tímidos, adivinen.
So the main point here is to answer to make sure that you're all there. Okay, so I've been open for 30 seconds. So let me end the poll. Okay, so here are the results. Okay, so I think most people got it right. In fact, the right answer is -2. Okay, great. So yeah, here it is. Okay, so now I don't just want to do topology, right? This is just a topological picture, and I don't have any regard for distance here. But if I want to have a hyperbolic geometry on my surface, then really I have to take the distance more serious. So let's take the disk model. Let's draw a nice regular octagon, and now we want to glue things in a way that when I put together all these puzzle pieces and add them up to a geometry, I have to have exactly the same point at each internal angle. I need these angles of the point where I glue up. This point gets identified into one point, just like the corner of the central point on the torus. And I need to have the sum of the internal angles to be equal to 2 pi. So since I have eight corners here that all get identified down to the same, I need these internal angles to be just pi over 4. And then everything glues up nicely, and I have here my recipe for gluing. So now I can use hyperbolic transformations to make these gluings, and I get a nice hyperbolic surface of genus 2. And we know that we can represent these isometries by matrices, because we saw that. and we can now go away, all of us, and spend the rest of the day playing hyperbolic Pacman if we know how to program that. I don't, so I'll keep talking for a little while. So I think I have, what, another 5 minutes or so?
I think, I don't know. Does everybody agree? ¿Todos tienen 5 minutos más?
Please go ahead.
Great.
I do. Go ahead.
Okay.
Fantastic.
Okay. All right. So let's see. So let's move on then, and yeah. So here's the formal version of this. So this was really the same. Okay. So let's try to see how many hyperbolic surfaces. So really, we just need to match up properly the sides and the internal angles. And one thing that's easy to see, if we have these 4 isometries represented by these 4 matrices, when we go all the way around and make this combination, A1, B1, which is the commutator, defined like this, and then A2, B2, this corresponds basically to go all the way back, and you can have fun realizing that that will be the identity. So this is certainly a necessary condition. Is this necessary condition sufficient? No, it's not. You can easily find this kind of matrices satisfying this relation, but you need some other condition on your set of matrices. And the condition you need is that they form what's called a Fuchsian subgroup of SL2R. So fine name for simple way of explaining that is that it's discrete, meaning that if you start looking at the whole group generated by these matrices, so you take all possible products of all sequences of these matrices, you don't want that to accumulate anywhere. You want that to form a nice, like the nice set of points you saw there in the parallelograms and Euclidean plane, so that you don't mess up your surface and it becomes curled up or non-smooth. So how do we take that? Well, again, topology actually can tell us something, because inside our group SL2I, we have a circle. This just comes from the rotations. Rotations in 2 forms a circle, right? So this is what this picture is supposed to transmit to you. So we have a circle inside SL2I. Now, over the circle, we can actually have a copy of the real line. We just wind the real line along the circle using these way of writing things, right? Theta could be a number in R. And it turns out that you can do exactly the same thing in SL2R. So just as we can wind the real numbers around the circle, there is a set, which is this kind of a group, which is made up by pairs of a matrix and kind of an angle, which covers the group of 2 by 2 matrices of determinant 1 just the same way as the real line covers the circle. Okay, so there's a construction of that. That's not so important for what I'm telling you, just to give you the idea about what you can do. Important point is that, in fact, what happens is that if for each matrix here, how many sit matrices, or how many elements of this SL tilde sits over it? Well, if we go back here, we know there's over the circle, we have all the real numbers modulo integer multiples of 2 pi. And here the situation is exactly the same. Okay, so let's just pass by that, and let's see in general. So this could be just A1, B1, A2, B2, but in fact you can do it for any genus. So if we have this set of matrices which potentially define a hyperbolic surface, there's a way of associate a kind of a winding number to this set of matrices. And what do? We simply take lifts of these matrices up to this SL tilde group, just as if, for instance, we were looking at rotation matrices, we could take some real number representing the angle modulo 2 pi. So we take up these lifts, but then we use that there's already this fine multiplication defined upstairs in this SL tilde group, just as there's the sum of numbers in R. And you can calculate actually this product of the lifts, of the commutators of the lifts. You know that the matrices themselves, the commutators multiply to R, to the identity matrix. So this commutator here, product of commutators, will have to go to the identity matrix. So basically it corresponds to a real number. Okay, that's some distance from the origin, just as if you lift a loop going 3 times around the circle. You can lift it up 1, 2, 3, and you see there's three winds between it, and this is what you can do, and you get an integer invariant of your 2G tuple of matrices, which is called the Toledo invariant. So here's our answer. In fact, we know that this invariant in absolute value is less than genus minus 1. So in case genus is 2, it's less than or equal to 1, and the group is function if and only if this invariant is actually basically max, well, in this case, minimal. And finally, they can be joined. So this again has a topological interpretation. We can think of the whole set of these tuples of matrices satisfying the relation, and then there's a natural equivalence, which is this one, which is not so important right now, but this parameterizes hyperbolic surfaces. And this Goldman theorem can be said that this topological space, in fact, basically has a connected component of consisting entirely of these so-called Fuchsian groups, which define for you hyperbolic surfaces. Okay, so basically, I've come to the end of my time and also to the end of the talk. In fact, these kinds of questions are really, let me just finish with that to make sure that I transmit that final message that mathematics and geometry is alive and well, and a lot of things are still out there to be discovered. And one of the things that people are working on that I'm interested in also is try to find out, to study similar questions, analogous questions for other real groups, non-compact groups of matrices. Okay, so thanks a lot for your attention. Thanks for your patience. So I think for me,
thank you, Peter. Okay, questions?
Thank you,
comments?
Peter.
Any questions?
Well, no question, but a comment. Something.
Esa es Alma, yo creo.
Yeah, Alma say that she's a little scary. I don't know why. Geometry is not scary at all. Peter, I just want to thank you because when somebody that loves geometry talks like you have done, actually I want to leave the office now and stop being that chair and get back into enjoying geometry. I just want to say thank you. Really, I enjoy it a lot. You take it from very simple, from something very simple to something very deep in just an hour. I like it very much.
Well, thank you. Thanks. I hope I, more or less, I'm sure that for some of you there was a bit too elementary, but on the other hand, I hope that maybe there were some students around also. That
there were, yeah. There were
and I hope they will be planning already on flying. You know, we don't want them we don't want them anymore around here in Costa Rica. Portugal is very nice, people.
Yeah, it is.
Well, you're more than welcome, certainly.
Thank you. Thank you very much for your talk, Peter. I love it as well. It was fantastic. Okay, if there are no more questions or comments, let's thank Peter again. And I think this is the last colloquium of the year, right? So
I think so. Yes, it is.
Thank you so much, Peter. You can clap if you want.
Actually, there's another talk this week. Next week.
In the colloquium? Oh, yeah?
Yeah, on Monday.
On Monday? Okay, thank you, Rafa.
Sorry, we missed. Okay.
I miss it too. Okay. Great. Okay, so.
Okay, so thanks a lot. It was a pleasure.
Thank you so much, Peter.
Thank you, Peter. It's really nice to see you again.
Yeah, nice to see you too.
I hope to see you here in Costa Rica. I think it's better.
Yeah.
Okay.
Maybe you can visit us sometime.
Yeah, certainly.
After pandemia.
Yeah.
Yeah.
Yeah, when things come back to normal.
When things get back to normal, yeah.
Yeah.
That will be fantastic.
Let us all hope 1 year from today.
Yes.
Yeah. Probably 6 months.
Yeah, let's hope so. Let's hope so.
Yeah. Good. Okay. Thank you, everybody. Have a nice Thursday afternoon. And thank you, Peter.
So, okay. So,
Bye.
Nice seeing you around. So, give my best to your family too.
Thank you. Give my best to your family too, to Sophia and you.
Thanks again. Will do, yes. And thanks again for the invitation.
Great.
Thank you very much, Peter.
pleasure. Bye bye.
Keep in touch.
Will do. Yes, you too.
Bye bye.
Bye bye.
Get